Nuclear fuel rods are among the most tightly regulated and precisely engineered components in the modern energy world, quietly powering cities for years at a time inside nuclear reactors while operating under extreme heat, radiation, and pressure. Yet behind their calm appearance is a complex industrial process that transforms mined uranium into ceramic fuel pellets and then seals them inside robust metal cladding, designed to perform flawlessly for decades. What looks like a simple metal tube is actually a highly controlled energy system, where every gram, dimension, and material property matters. And today on the How Factory, we're stepping inside specialized nuclear fuel facilities to see how nuclear fuel rods are manufactured for power plants, from raw uranium to reactor-ready assemblies. The story of nuclear fuel begins long before it reaches a power plant. Uranium was discovered in the late 18th century, but its energy potential wasn't understood until the 20th century, when scientists learned that splitting uranium atoms could release enormous amounts of heat. After World War II, this knowledge was redirected towards civilian power generation, leading to the development of nuclear reactors designed to use controlled fission to produce electricity. From the beginning, fuel manufacturing had to meet standards far beyond those of ordinary industrial products, because once fuel is placed inside a reactor, failure is not an option. The process starts with uranium mining. Uranium ore is extracted from the ground using open pit, underground, or in situ recovery methods, depending on the geology. The ore itself contains only a small percentage of uranium, so it must be processed. At milling facilities, the ore is crushed and chemically treated to separate uranium from waste rock. The result is a concentrated powder known as Yellowcake, which is chemically uranium oxide. At this stage, the material is radioactive but relatively low in activity and can be handled with standard industrial precautions. Yellowcake is not yet suitable for fuel use. It is transported to conversion facilities, where it undergoes chemical processing to become uranium hexafluoride. This compound is unique because it can exist as a solid or gas at relatively low temperatures, making it suitable for enrichment. Most nuclear power reactors require uranium enriched in the isotope uranium-235, which is more likely to undergo fission. Natural uranium contains only about 0.7% uranium-235, so enrichment increases this concentration to typically between 3 and 5% for power reactors. Enrichment is performed at specialized facilities using methods such as gas centrifuges. Uranium hexafluoride gas is spun at extremely high speeds, separating lighter uranium-235 from heavier uranium-238. This process is highly regulated and monitored internationally. Once enrichment reaches the required level, the uranium hexafluoride is converted back into a solid form, suitable for fuel manufacturing. At fuel fabrication plants, enriched uranium hexafluoride is chemically converted into uranium dioxide powder. This fine black powder is the basic building block of nuclear fuel. From here on, the focus shifts from chemistry to precision manufacturing. The powder must be transformed into fuel pellets with exact dimensions, density, and purity. Even tiny defects could affect how the fuel behaves inside the reactor. The uranium dioxide powder is carefully blended to ensure uniformity, then fed into pellet presses. These presses compress the powder under high pressure into small cylindrical shapes known as green pellets. At this stage, the pellets are fragile and chalk-like. Their dimensions are slightly larger than final size because they will shrink during sintering. Sintering is one of the most critical steps. Green pellets are loaded into high-temperature furnaces and heated to temperatures exceeding 1,700 degrees Celsius in a controlled atmosphere. During sintering, the powder particles bond together, increasing density and strength while reducing porosity. The pellets shrink and become hard, ceramic-like solids capable of withstanding extreme heat and radiation. Furnace conditions are carefully controlled to achieve the correct microstructure, because pellet density affects heat transfer and fission behavior inside the reactor. After sintering, the pellets are cooled and inspected. Automated systems measure diameter, height, weight, and density. Pellets that fall outside tight tolerances are rejected. Accepted pellets may then be ground using precision machines to achieve exact final dimensions, often accurate to microns. This ensures uniform spacing inside the fuel rod, which is critical for predictable heat generation. Quality control at the pellet stage is exhaustive. Samples are tested for chemical purity, grain structure, and mechanical strength. Pellets are also visually inspected for cracks or chips. Because pellets will be stacked inside sealed rods and left in a reactor for years, reliability is non-negotiable. Once pellets are approved, they are ready to be loaded into fuel rods. Fuel rods begin as long tubes made from specialized metal alloys, most commonly zirconium-based alloys known as zirconium cladding. Zirconium is used because it is strong, corrosion-resistant, and absorbs very few neutrons, allowing the nuclear reaction to proceed efficiently. Producing zirconium cladding is itself a complex metallurgical process involving purification, alloying, extrusion, and precision machining. The zirconium tubes arrive at the fuel plant, cleaned and inspected. Before loading, one end of each tube is sealed with a welded end cap. The tube is then positioned vertically, and uranium dioxide pellets are stacked inside using automated loading systems. The pellets are loaded with precise spacing, sometimes with small springs or spacers, added to maintain proper alignment and accommodate thermal expansion during reactor operation. Once loaded, the open end of the tube is sealed with another welded end cap. Welding is performed using highly controlled techniques such as laser or resistance welding to ensure a perfect, leak-tight seal. Each weld is inspected using non-destructive testing methods like X-ray or ultrasonic inspection. The integrity of these seals is critical because the cladding is the first barrier preventing radioactive material from escaping. After sealing, the fuel rods undergo additional testing. Helium leak tests check for microscopic leaks. Dimensional checks verify straightness and length. Surface inspections look for scratches or defects that could compromise corrosion resistance. Only rods that pass every inspection move forward. Individual fuel rods are not used alone. They are assembled into fuel assemblies, large structural frameworks that hold dozens or even hundreds of rods in precise geometric arrangements. The design of a fuel assembly depends on the reactor type. Assemblies include spacer grids that keep rods evenly spaced and allow coolant to flow efficiently between them. Structural components are made from corrosion-resistant alloys designed to withstand years of radiation exposure. Assembly is performed in clean, controlled environments. Robotic systems and skilled technicians position rods into grids with millimeter precision. The completed assembly is then inspected for alignment, structural integrity, and cleanliness. Any debris or misalignment could interfere with coolant flow inside the reactor, so cleanliness standards are extreme. Once assemblies are complete, they undergo final inspections and documentation. Every fuel rod and assembly is tracked by serial number. Detailed records document material composition, enrichment level, manufacturing conditions, and test results. This traceability allows operators to monitor fuel performance throughout its entire life cycle. Finished fuel assemblies are transported to nuclear power plants in heavily shielded containers designed to withstand severe accidents. Transport is regulated and escorted with constant monitoring. At the plant, the fuel is stored securely until it is loaded into the reactor during scheduled outages. What makes nuclear fuel manufacturing remarkable is the combination of industrial scale and microscopic precision. A single fuel pellet is only about the size of a fingertip, yet it contains enough energy to power a household for years. Hundreds of these pellets, sealed inside rods and arranged into assemblies, quietly generate massive amounts of electricity without producing carbon emissions during operation. Safety and quality culture dominate every step. Unlike most manufactured products, nuclear fuel is designed to perform reliably for years without maintenance in one of the harshest environments engineered by humans. This is why manufacturing tolerances are so tight and inspections so relentless. From mined uranium ore and chemical conversion to ceramic pellet production, from zirconium cladding and precision welding to full fuel assembly construction, the journey of nuclear fuel rods is one of the most carefully controlled manufacturing processes on Earth. And that is how nuclear fuel rods are produced, inspected, assembled, and delivered. transforming raw uranium into the engineered fuel that powers nuclear reactors and supplies reliable electricity to millions of homes. Thanks for watching the How Factory.